So level 4.5 is starting with real zeros of a polynomial. So what we were doing in 4.1 was we were given the zeros and we had to build the polynomial. Here, I'm giving you the polynomial and I'm asking you to find the zeros out. So in order to do this, we need to remember what long division does for us. So just as a quick note from 8.4 and 8.3, when we have division, it's the quotient times the divisor plus the remainder equals our dividend, or what's going to be underneath. And that's going to play a pretty key role because we're going to use the first thing called the remainder theorem. So I'll read it and then we'll figure out what that means. So let f be a polynomial. If f of x is divided by x minus c, then the remainder is just f of c. So what does this mean? If I'm dividing by a linear pair, divide by a linear binomial, all you have to do is plug in c, or the opposite, and that will be your remainder. Plug in c to find your remainder. So let's just try that out. We're going to use the remainder theorem to figure out if we did this division, if we divided this polynomial by x minus 3. I'm saying from the remainder theorem, if we did the division, it would be the same thing as just plugging in 3 to our function. And if we plug in 3, that's 3 cubed minus 4 times 3 squared minus 5, or 27 minus 36 minus 5. So 27 minus 36 is negative 9, minus 9 is negative 14. And just a quick check, if we did this synthetic division, that would be a 3 on the outside, and then 1, negative 4, 0, negative 5. I'm saying if we did this division, we would get negative 14. So we bring down the 1, multiply, so that's negative 1, multiply, add, multiply, add. So this remainder theorem, these two are the same. Let's try just one more. So dividing this polynomial by x plus 2. So if I do that, all I'm asking you is plug in negative 2. So that would be negative 2 cubed minus 4 times negative 2 squared minus 5. Or negative 8 minus 4 times 4 is 16 minus 5. So negative 8 minus 16 minus 5, which is negative 29. And again, just as proof, if I had negative 2 on the outside, and this pen's going to die on me, and again we had 1, negative 4, 0, and negative 5, bring down the 1, negative 2, that would be negative 6, that would be 12, that would be negative 24, which makes negative 29. So negative 29 is my remainder, and that's negative 29 is also my remainder if I use the remainder theorem. So one step further with the remainder theorem is something called the factor theorem. So the factor theorem says, almost identical, let f be a polynomial. Then x minus c is a factor if and only if the remainder is 0. So if you plug in c and the remainder is 0, then the remainder is 0, then x minus c is a factor. Or c is a 0. And that's what we want. We're going to be looking for our zeros because that's how we build our polynomials, and that's how we solve our polynomials. So let's just quickly see. Use the factor theorem to determine if this function has a factor x minus 1. So to figure out if it's x minus 1, we're going to plug in 1. So for a, we're going to plug in 1, and we're going to see if it comes out to be 0. So if I plug in 1 to this function, I get 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. So that's 2 minus 1 plus 2 minus 3. So 2 minus 1 is 1. 1 plus 2 is 3. 3 minus 3 is 0. So what we just showed is x minus 1 is a factor of f of x. So is a factor. Because the remainder is 0. That's the factor theorem. So let's try b. If I plug in negative 3, because we do the opposite sign, we're going to plug in negative 3. So we get 2 times negative 3 cubed minus 3 squared, negative 3 squared, plus 2 times negative 3 minus 3. So this cubed gives us negative 27 times 2 minus, that is 9 minus 6 minus 3. I don't even have to go any further with this because that would be negative 54. A negative and a negative and a negative and a negative does not equal 0. So without having to work this out, by checking the factor theorem, x plus 3 is not a factor. So that's the factor theorem, which is an application of the remainder theorem. All right, let's flip it over. So the next theorem that we're going to add, which doesn't really have a nice name, makes a lot of sense. So I'll read it. A polynomial function cannot have more real zeros than its degree. So if we have a degree of 3, we're going to have at most 3 real zeros. We can't have 4 real zeros for a degree of 3. Or if our degree is 5, at most we'll have 5 real zeros. So this helps us figure out how many zeros we're going to have. Same thing with the next thing. So Descartes' rule of sign. Descartes, his name is René Descartes, is a famous French mathematician. If you want to Wikipedia him, he actually has done a lot of things, including the XY coordinate plane is called the Cartesian coordinate plane, named after René Descartes. So he has provided us information about the number of positive and negative real zeros of a function. So positive and negative real zeros. This is another way of figuring out how many of these we have. So how many and what type? The two types are either positive or negative. So this is what we do. We look at the number of sign changes. So what we mean by sign changes is where it goes plus to minus or minus to plus. When the sign changes, we call that a sign change. So if we just look at our function as a whole, how many sign changes are there? So we go from negative to positive, so that's 1. Positive to positive, that doesn't change. Positive to negative, that's 2. And then negative to negative, so that doesn't change. So there are 2 sign changes. What about if we plugged in a negative x? So wherever we see a odd exponent, I'm going to change the sign. So f of negative x would be 3x to the 7th, because that negative changes, plus 4x to the 4th, because that's to the 4th, so the negative doesn't get changed, plus 3x squared, so that doesn't change, plus 2x, because that's an odd exponent, minus 1. So how many sign changes does this have? Positive to positive, positive to positive, positive to positive, positive to negative. So this one has one sign change. So these sign changes tell me everything that I need to know about the type of zero that I'm going to get. And we're going to clarify this in just a second. So let's just see, how many sign changes does this polynomial have? So we just look at it normally. That is positive to negative, negative to positive, so that's 2, positive to positive, positive to negative, so that's 3, negative to positive, that's 4. So this has 4 sign changes. If we change the signs on all of the odd exponents, then f of negative x would be negative x to the 5th minus x to the 4th, because that stays the same, minus 3x cubed, that changes, plus 9x squared, plus x, plus 5. Now we look again at the sign changes. So from negative to negative, doesn't change. Negative to negative, doesn't change. Negative to positive, that's one sign change, sorry. Positive to positive, positive to positive. So there is one sign change. So this is what Descartes' rule of signs gives us. Given a polynomial written in standard form, and standard form is largest exponent first, and then it descends. The number of positive real zeros is either equal to the number of variations in the sign or an even integer multiple less of the number of variations. So if there are 5 sign changes, then there's either 5 or 3 or 1 positive roots. So if we looked back up at here, so the first one we did, this had 2 sign changes, so there are either 2 or 0 positive zeros, or x-intercepts. Likewise, there's 1 sign change here, so there has to be 1 negative 0. We can't go down an even integer from that. So then we read the second part. The number of negative zeros of f is either equal to the number of variations of sign of the coefficients of f of negative x. So that's why we plug in that negative to figure out how many negative integers we have. Sorry, zeros we have. So again, we look at the example above. There are 4 sign changes. So that means we have, I'm going to write this in a different color, we have 4 or 2 or 0 positive zeros. And we have 1 sign change when we plugged in our negative. That means we have 1 negative 0. So again, this is helping us classify what type of zeros that we have. We're not figuring out yet what they are, but we're figuring out how many. So we're going to use the theorem at the top, which means we have no more than the degree. So if we look at this, there are 7 possible real zeros. We know that either 2 or 0 are positive, and we know that 1 is negative. So that leaves 4 zeros that are not real. We're only going to have at most 3 real zeros. Hopefully that makes sense. So let's flip it over and try out some problems. So example 3. Using Descartes' rule of signs, determine the number of real solutions for this polynomial. So the number of real solutions. We want to figure out how many positive zeros I have and how many negative zeros I have. So positive zeros. We just look at the sign change. So positive to positive, nope. Positive to positive, still hasn't changed. Positive to positive. Positive to negative, so that's 1. Negative to positive, that's 2. Positive to positive, positive, positive. So there are two sign changes. So then we either have 2 or 0 positive zeros. And when we say zeros, the other way of saying is solutions. So we have zeros, we have solutions, we have roots. All of those mean the exact same thing. To find out how many, remember this is a how many question. How many negative zeros? We're going to find out what f of negative x is. And f of negative x is, we're going to change all the odd signs. So that's negative 4x to the 7th plus 3x to the 6th, that stays, minus x to the 5th, that changes, plus 2x to the 4th, that stays the same, plus x cubed, because that changes, plus 9x squared, I didn't leave myself enough room, minus x plus 1. So we look at our sign changes. Negative to positive, 1. Positive to negative, 2. Negative to positive, 3. Positive to positive, no. Positive to positive, no. Positive to negative, 4. Negative to positive, 5. So there are 5 sign changes. Therefore, that's what those 3 dots mean. There are 5, 3, or 1 negative zeros or solutions. So that's how we use that to figure out how many we have. And that's going to help us with the next theorem. And this is the super important one. It's called the rational root theorem. The rational root theorem states if you're given a polynomial of any degree, and it's written in standard form. So I know I wrote this in 4.1, but here is what the book writes. So a to the n, x to the n, so the degree n, plus a to the n minus 1, x to the n minus 1. So it just drops down a term, plus dot, 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 which means yada, 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 plus a sub 0, which is our last term. And each of those are integer coefficients. So if a sub 0 and a sub n are non-zero, then each rational solution written as a fraction, x equals p over q, in lowest terms satisfies, this is what p is an integer factor and constant term, and q is an integer factor and constant term. So what does that mean? That's super complex. Well, if you can look at our polynomial, so this is what it means. We can write p and q are our first number and our last number. P is all the factors of the last term, plus or minus, over q, which is all the factors of the first term. So it's always first term factors over the last term factors. This gives us a list of all of the potential zeros or roots or solutions for a polynomial. So let's try it. I want you to list the potential zeros of this polynomial. So p is 6 and q is 2. So all of my potential zeros would be plus or minus all of the factors of 6. So 1 and 6, 2 and 3, divided by factors of 2, 2 and 1. Or, if you want, 1 and 2. So all of the zeros would be 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1. So our potential zeros are plus or minus 1, 2, 3, and 6. And then fractions. 1 divided by 2. 2 divided by 2, which is 1. 3 divided by 2. And 6 divided by 2, which is 3. This list, plus or minus, gives me all of the potential zeros. Now you're saying, well, how do you find out which one is the zero? Well, we use the factor theorem, plug it in, see if it comes out to be 0. Let's try another one. Find all of the possible rational x-intercepts of this function. So I want to know, what's p? P is 12, so I'm going to write all of the factors of 12. 1 and 12, 2 and 6, 3 and 4. And I'm going to divide that by all of the factors of q, which is 1. So this is your p, this is your q. So really my list is everything over 1. So plus or minus 1, 2, 3, 4, 6, and 12. This is all my potential zeros. How do I know how many positive zeros or negative zeros? We use Descartes' rule of signs to help us narrow our guess down. And how many total zeros does it have? At most 4 real zeros. So we're going to start piecing all of this together. So C, find all of the potential x-intercepts. So I want to know what's my P, which is 5, what's my Q, which is 2. So my P's over Q's is plus or minus 1 and 5, comma, 1 and 2. So my list is plus or minus 1, 5, that's 1 divided by 1, 5 divided by 1, 1 half, and 5 halves. All of these are my potential zeros for this. All right, let's flip it over. So D is one more of these. It's a little more involved. Use the rational root test to find all the possible rational zeros of this function. So what are my P's? What are my Q's? My P is 30. That's P. That's Q. Q is 6. So here, factors of 30 is plus or minus 1, 30, 2, 15, 3, 10, 4 doesn't go into 30, 5, and 6, 7, 8, 9, 10. All over factors of 6. So 1, 6, 2, 3. Okay, so if we're generating our list, we're going to write everything over 1. So our list is plus or minus 1, 2, 3, 5, 6, 10, 15, 30. Then we divide everything by 2. So 1 half. 2 divided by 2 is 1, so that's included. 3 divided by 2. 5 divided by 2. 6 divided by 2 is 3, that's included. 10 divided by 2 is 5, which is included. 15 divided by 2. 30 divided by 2, which is 15, which is already included. Then we divide everything by 3. So it's 1 over 3, 2 over 3, 3 over 3 is included, 5 over 3, 6 over 3 is included, 10 over 3, 15 over 3 is 5, 30 over 3 is 10. Okay. And then everything over 6. So 1 over 6. 2 over 6 is 1/3. 3 over 6 is 1 half, which is included. 5 over 6. 10 over 6, which is 5/3, which is included. 15 over 6, which is 15 over 6, which would be 5 halves, which is included, and 30 over 6 is 5. So this monstrosity is our list of all potential zeros. Not all our zeros, they're potential zeros. So then how do we go about narrowing this list to figure out? Well, we know that there's a maximum of 4 zeros because the degree is 4. So 4 of these numbers could work. Then we use Descartes' rule of signs to figure out how many positive and how many negative zeros we have. And then we're going to use the rational root theorem. So if you look at what I'm saying, step 1, use the degree to figure out the degree of the polynomial to determine the maximum number of zeros. We can do that. We can use Descartes' rule of signs to figure out how many positive zeros and how many negative zeros. We can do that. Rational root theorem, we use that to determine which one of those are zeros. So we start picking from our list. We figure out which one of those is zeros. Once you find one of those zeros, we're going to do synthetic division. And then if we can reduce it down to a quadratic, we can factor those. So remember all of our factoring techniques that you knew to help find a polynomial. Because what we want to boil it down to is all of the factors and then figure out which one of those are zeros. So this next page is just doing those types of problems. So example 5, this is going to be a process. We want to find all of the real zeros of this polynomial, and we want to write it in factored form. So we want to find the zeros, and then we want to write the polynomial completely factored out. So we look at the degree. The degree here is 5, which means we have at most 5 real zeros. We're going to do Descartes' rule of signs. So rule of signs to check how many positive, how many negative. So 1, 2, 3, 4, 5 sign changes. So 5 sign changes. That means we're going to have 5 or 3 or 1 positive zeros. Likewise, we're going to switch all the negatives, so that would be negative x to the 5th minus 5x to the 4th minus 12x cubed minus 24x squared minus 32x minus 16. So that's negative, 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 negative. So we have 0, negative zeros. So that's super helpful because if I know that all I have to look for are positive zeros, that saves me a bunch of time. So then next up, what are my p's and q's? So my p over q is factors of 16. So 1, 16, 2, 8, 3, no, 4, yes, 4 and 4. That's it. All over 1. And I should write plus or minus, but I know that I have 0 negatives, so all I need are positive zeros. So my potential list to check, 1, 2, 4, 8, and 16. So I've already narrowed it down. Potential 5, these could be all 5. We could have repeats. So it's important that each step we check to figure out what happens at each spot. So we're going to do, let's try 1 first. And then we're going to write out our synthetic division. So we have 1, negative 5, 12, negative 24, 32, negative 16. Bring down the 1. Multiply, add. 1, which is negative 4, 8, 8, negative 16, negative 16, 16, 16, 0. So, hey, that worked. First time through. That means that x minus 1 is a factor. Okay, so our new polynomial is, I'm going to write this in a new color, that is x to the 4th minus 4x to the 3rd plus 8x squared minus 16x plus 16. We dropped it down 1 power. We have to test again. Well, if we look, 1 and 16 are still our factors, so our list is still the same. So I want to retest. Let's try 1 again. See if that repeats. So if I try 1, I'm going to have 1, negative 4, 8, negative 16, 16, which is 1, 1, negative 3. All right, this doesn't look good. That's 5, 5, negative 11, negative 11, which gives us 5 as a remainder. So for this polynomial, 1 doesn't work again. So let's try 2. So 2, 1, negative 4, 8, negative 16, 16. So 1, multiply, add, negative 2, negative 4, and that's 8, which is negative 8, which is negative 16, which is 0. So x minus 2 is a 0. So that helps. So now we have to figure out, again, well, we already figured out 1 doesn't work. So we have to do another division. So let's try 2 again, see if that works. So I'm going to just do the same synthetic division. Bring down the 1, multiply, add, which is 0, multiply, add, which is 4. 2 times 4 is 8, add, which is 0. Well, all right. So x minus 2 is another factor. Again, this was a x to the 4th, so this is a x to the 3rd. So this is x squared. So currently, this is x squared plus 4. Well, x squared plus 4 is unfactorable because it's not a difference of 2 squares. So we have 3 positive zeros, and the factors of this whole polynomial would be x minus 1, x minus 2 squared, and then x squared plus 4. This is unfactorable. So this is our solution. All right, so C, because B is a repeat, and I should catch that, we're going to do the exact same thing. So the degree is 4, so that means 4 at most 4 real zeros. Okay, rule of signs. We go positive to negative, so 1, negative to positive 2, positive to negative 3, negative to negative is nothing. So 3 or 1 positive zeros. If I switch this, then that'd be negative x to the, that'd be x to the 4th plus x cubed plus 2x squared plus 4x minus 8. So positive, 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 negative. So we have 1, negative 0. All right, so that helps me out a lot. So now, based off of this, what's my P and what's my Q? So all my factors of 8, so plus or minus, 1, 2, 4, and 8, all over 1. So here, my list is going to be plus or minus 1, 2, 4, or 8. So remember, I'm going to have 3 or 1 positive zeros and 1, at most 1, negative zeros. So we're going to have to start guessing. So I can start with 1. So if I do 1, I'm going to write that on the outside. That's going to be 1, negative 1, 2, negative 4, negative 8. Bring down the 1, 1, 0, 0, 2, 2, negative 2, negative 2, negative 10. So 1 is not a 0. So that didn't work. So how about 2? Let's try 2. So that's 1, negative 1, 2, negative 4, negative 8. So bring down the 1, 2, That's positive 1, 2, 4, which is 8, which is 4, which is 8, which is 0. All right, so that means x minus 2 is a factor. Well, okay, how do we figure out what would be another factor here? Could we guess 1? Well, no. We already found out that 1 doesn't work. So how about a negative 1? So we could try negative 1. And I'm going to do that with this synthetic. So I'm going to use these same numbers. So that bring down the 1, which is 1 times 1 is negative 1. So negative 1, which is 0. Negative 1 times 0 is 0. 4. Negative 1 times 4 is negative 4, which is 0. All right. So x plus 1 is another one of my zeros. And that takes care of my 1, negative 0. Well, this, again, is x squared plus 4, because this is 4th degree, this is 3rd degree, so that's 2nd degree. So my zeros, I have 1 positive, 1 negative, and then this, which is unfactorable. So my answer is x minus 2, x plus 1, and x squared plus 4. And my real zeros are x equals 2 and x equals negative 1. So last up, I know this has been quite a long level. I want you to solve, so tell me what the real zeros are. So this is saying find real zeros. So the degree is 3, so at most 3. Sign changes, there are 0 sign changes, so then no positive zeros. Okay. If we switch the signs, that would be negative 2x cubed plus 3x squared minus 2x plus 3. So the 1, 2, 3. So there's 3 or 1 negative zeros. Okay, so that gives me some information. So what are my p's over q's now? That's going to be plus or minus 3 and 1, and then 1 and 2. So my list is going to be plus or minus, well, we know there's no positive, so all we're checking are minus. So negative 1, 3, and then 3 halves. So negative 1, negative 3, negative 3 halves. All right, so now this is just a guessing game. We can start with negative 1 and see what we get. So negative 1, which is 2, 3, 2, 3. It's 2, negative 2, 1, negative 1. That's 1, which would be negative 1, which gives me 2. So that doesn't work. So how about 3? So negative 3. 2, 3, 2, 3. Bring down the 2. That would be negative 6. That would be negative 3. Positive 9. This is not looking good. Negative 33, which is something, which is not 0. So negative 1 doesn't work. Negative 3 doesn't work. So I'm sorry. The only answer is going to be a fraction because we're down to negative 3 halves. So if we do negative 3 halves, that's 2, 3, 2, 3. Bring down the 2. Multiply these two, we get negative 3, which is 0, which is 0, which is 2, which is negative 3, which is 0. So then our remainder is 2x squared plus 2. So then that means that x equals negative 3 halves is a 0. If I wanted to factor this, that would be x squared plus 1. Since there's a plus sign, no real zeros for this. So the only solution is so that is finding all of the real zeros of a polynomial. The problems are right here. Good luck.